Hello and welcome to Q Calculations video. Today we're going to look at a couple different physical quantities that we use to determine changes of heat in a sample. The first one we're going to look at is something called heat of fusion. Fusion is actually another word for melting. So this is the amount of heat needed to convert a mass of a substance from solid to liquid. What's important to understand about this is even though fusion specifically kind of means melting, heat of fusion can be this phase change in either direction, meaning it can be solid to liquid or it can be a liquid to a solid. So again, this is the amount of energy or the amount of heat needed to convert a mass of substance from a solid to a liquid. If we're going from solid to liquid, that heat would be put in. If we're going from a liquid to a solid, that heat must be removed. The reason that this heat is necessary is because there are intermolecular forces between the separate molecules. So if we have a sample of ice, which is shown in this picture, we have all these little interactions right here that must be essentially broken. So there's potential energy needed to break those intermolecular forces. If we have a sample of water, we actually have to get those liquid molecules to line up properly so that those associations are able to form. So that involves us removing a certain amount of potential energy from the sample. So there is a potential energy change here, which we see on those energy diagrams that we've already looked at. And that's what we define in this case as the heat of fusion. So again, if we look at that flat region on the graph, you're going to see, oh, we're putting heat in, but nothing's happening. If you were looking at a cooling curve, you'd see it looking like that instead. But that amount of energy right there that I've labeled as the heat of fusion is when melting is occurring and that energy change that we have there. I'd not really put a box for you to write this down, just kind of an explanation so you make sure that you understand that there is a relationship between that stretch on the graph and the calculations that we're doing today. So if you look at table T on your reference table, we have what are called the heat calculations. The first one that we're going to use is going to be for when we have heat, when we're dealing with calculations involving heat of fusion. So this is Q equals MHF. Q is heat, and that's in the unit of joules. If you're unsure of units, they are listed on table D. M is mass in grams. And heat of fusion is a constant that is in the unit of joules per gram. And this is actually for water found on table D. There are other substances that are not on there, and you can do calculations with those. That value does have to be given to you at that point. So this is when we do anything like freezing, fusion, melting, solidification, whether or not we're adding or removing the heat doesn't matter so much in the calculation. We just have to understand it's the same quantity of heat, it's just whether or not we're adding or removing it. So we want to know how much heat is needed to melt a 200-gram sample of ice. So we're going to write down what we know first. We know that we have a mass of 200 grams. It's very important in these to look at your verb. So because we see the word melt here, that clues us in that we're going to be using heat of fusion. So even though this is not given the problem, it is kind of considered a known because we can easily look it up. And it's 340 joules per gram. What we are solving for is our Q in joules, and we know this from the word heat in the problem. So we're going to use Q equals MHF. So our mass again is 200 grams, 334 joules per gram. And we can go ahead and solve this. Get 66,800 joules. And again, there's 3 sig figs here. That's why you have that decimal place following the 200 grams. If you're really into dimensional analysis, just can't get enough, you can also take your starting amount in this problem, your 200 grams, and you can say to yourself, hey, I want to end up in joules. And in this case, what we can do is simply plug in 334 joules to melt 1 gram. joules cancel, and essentially, or I'm sorry, grams cancel, and essentially you're doing the exact same math. So this formula does the same thing that dimensional analysis would do. If we have a sample, or I'm sorry, if 167,000 joules of heat is needed to melt a sample of ice, what is the mass of the sample? So here they're giving us Q. We still know that we have the word melt here, so that still tells us that we'll be using heat of fusion. Our unknown in this case is mass, which will come out in grams. So this is still Q equals MHF. So in this problem, we're going to go ahead and divide to get 500 grams. And again, if you wanted to tackle this with dimensional analysis, you're starting with joules. In this case, you'd have 334 joules on the bottom, 1 gram on top, which would tell you that you're dividing, and you get the same answer. Heat of vaporization is the exact same concept. The only change here is that it's a different phase change involved. So what's going on in this phase change, this is the amount of heat needed to convert a mass of a substance from liquid to solid. So again, this is the same idea of just a major change in intermolecular forces. If we want to vaporize a sample, we have to put energy in. If we want to condense a sample of vapor, we have to remove energy so that those associations can form. It requires potential energy to break intermolecular forces. And when we form new intermolecular forces, potential energy is released. Now, what's interesting about heat of vaporization is that if we look at a typical heating curve, cooling curve for a substance, we are going to notice that if we compare B, which is the heat of fusion, to D, this is the heat of vaporization, D is a much longer stretch of the graph. It takes a lot more energy to vaporize something than it does to melt it. If you think about what happens when you go and try to boil some water on the stove, it takes a few minutes for that to get going. Whereas, you take an ice cube out of the ice cube tray, it begins to melt pretty quickly. Heat of fusion of water is 334 joules per gram compared to the heat of vaporization, which is 2,260 joules per gram. So not only does vaporization occur at higher temperature, so you go into it with more energy, but that's just, average kinetic energy, that's just temperature, but the process itself requires more energy as well. So if we look at the amount of energy that's put in during B versus the amount of energy that's put in during D, there's a pretty significant difference. So our calculation for this is actually extremely similar. Q equals mHV. Q is heat in joules, M is mass in grams, and HV is heat of vaporization in joules per gram. So this is exactly the same setup. We just have to make sure we know which formula we're using when we have these examples mixed together by seeing what's happening in the problem. So this is a liquid to gas or gas to liquid transition. So how much heat is needed to vaporize? So our big keyword that's important here is the word vaporize. That tells us what we're doing. A 200 gram sample of liquid water. So we know we have a sample that has a mass of 200 grams. And because we know we're vaporizing, we will be using heat of vaporization, which again is found on reference table B, 2,260 joules per gram. Our unknown is Q. That's heat in joules. So we're using Q equals mHV. So Q equals 200 grams times 2,260 joules per gram. And you'll probably notice I set this up to be very similar to look like one of the problems that we already did. You're going to get a huge number for this compared to when we looked at melting. So this requires 452,000 joules. So that's for a 200 gram sample. If we look back at one of the problems that we already did, in this problem we melted 200 grams and that only required 66,000 joules. Oops. So you will get a much larger number there. So if we have 113,000 joules of heat energy needed to vaporize a sample of water, what is the mass of the sample? So this time we know joules because of the word vaporize. We know we need to use HV. This time we're solving for mass. So we plug in this time, put our joules in for Q. Masses are unknown. And then we're going to go ahead and solve by dividing this time to get 50 grams. So I kind of saw this somewhere once and liked this graphic of the idea that, okay, you know, we're liquids in the middle. If we're going to solid, we're using heat of fusion. If we're going to or from gas, we're using heat of vaporization. Now, other calculations we can do with something called heat capacity have to do with changing temperature in a sample. So heat capacity is the amount of heat needed to change the temperature of substance. In America, we tend to measure heat with calories. What's important to kind of understand is, you know, I put some side information on here about food calories and that kind of stuff. What's important to understand in terms of chemistry is heat capacity depends on two factors. It depends on the chemical makeup of the material and the size of the sample. So how much heat it's going to take to change, you know, the temperature of a sample depends mainly on those two things. I like to kind of throw in this little factoid about food calories, which we'll talk about in the lab we're doing, because it's just kind of an interesting way to think about numbers. So if you eat 230 calories, you're really eating 230,000 chemistry calories. Kind of a fun thing to think about. If a substance has a high heat capacity, it's going to be really good at storing heat, tend to feel warmer, and require a long time to heat up. And you learn about this with water when you think back to earth science and learning about climate protection. You know, we live kind of near the Finger Lakes and Great Lakes, which does offer some climate protection to us in terms of keeping it a little bit warmer in the winter. A lot of people, you know, grow grapes near the Finger Lakes in order to make wine because we have that climate protection there. Substances with a low heat capacity do not store heat well and tend to feel colder. They do heat up really quickly though. So this is like metals, if you think about how quickly they heat up, that's due to their very low heat capacity. Specific heat capacity we'll be dealing with, which is actually more of a numerical quantity, where we talk about how much it's going to take to heat 1 gram of a substance, a temperature change of 1 degree Celsius or 1 Kelvin. So this unit can be given with Celsius or Kelvin interchangeably. The old reference tables actually use Celsius here, so just keep that in mind. It doesn't matter if it's Celsius or Kelvin in this particular unit because 1 degree change in either one is an equal quantity of heat. So I gave you a few different substances just to look at here. For comparison's sake, you can see that liquid water has an absolutely unbelievable heat capacity. So what's kind of nice to understand conceptually is that if I was to go and I had equal size 1 gram samples of each substance on the chart and I wanted to apply 1,000 joules of heat to each one, which sample would end up with the highest temperature? And the answer to that is mercury, because mercury has such a low heat capacity. Water would heat up the slowest, but water would also hold that heat the best. So even though the temperature change would be not as much, you know, that energy would stick in there a little bit. You know, and in terms of what this has to do with our weather, I did grow up next to Lake Ontario, and we do actually have a moderated climate living that close to a Great Lake. Sometimes it's not quite as hot in the summer there or quite as cold in the winter as it could be and might be in Syracuse. So our calculation here is a little bit more involved. So we still have heat in joules, mass in grams. C stands for specific heat capacity. again, this is in joules per gram Kelvin. And we are now going to have change in temperature. And this will typically be in Kelvin, although it could also be in Celsius. So please note that this is the only formula where you plug in temperature. So we will be plugging in a change in temperature here, which is different than the other ones where we have a set temperature, since temperature doesn't change during phase change. What is the amount of heat needed to raise the temperature of 65 grams of water from 298 to 312? So what we know here is that we have a mass of 65 grams. Sorry, I think I might have said 68 before. And we have a delta T of 15 Kelvin, so 313 minus 298. And because we know that we see right here that we're raising temperature, so temperature is changing, that tells me I'm going to use C, which is 4.18 joules per gram Kelvin from table D. Our unknown here is going to be Q. So we're going to plug in our 65 grams. I don't know why I keep writing the decimal there. It's not really necessary. 4.18 joules per gram Kelvin and 15 Kelvin. Oops, sorry, I guess I kind of did that all in one step. And you go ahead and multiply those to get 4,080 joules. So one more quick problem, wrap this video up. A sample of water is heated from 283 to 288 by the addition of 125 joules of heat. What is the mass of the sample? So to speed this along a little bit, I know this video has gone a little lengthy. We're going to do 145 joules equals an unknown mass, 4.18 joules per gram Kelvin. And last but not least, we've got to plug in that temperature change, which is 5 Kelvin. And when you solve for mass, you should get 5.98 grams.